Hi dear students, so in this lecture video I am going to derive element stiffness matrix for a beam element using Hermite shape function. Okay, so already we derived the element stiffness matrix for beam element with the help of what, the shape function. So in this we are going to derive the element stiffness matrix for using Hermite shape function. Okay, so shape function is different, Hermite shape function is different. So look at now I am going to derive the element stiffness matrix for this beam element. Okay, so the beam stiffness matrix based on the Euler-Bernoulli theorem. Okay, that we are going to derive now. Okay, so here the element stiffness matrix for the beam element is obtained by using what, the strain energy stored in the given beam, that already we studied in the module 1. Okay, so the strain energy stored in the given beam element, okay, which is given by this. Okay, strain energy induced in the given beam element is equal to what, strain energy is denoted by u. Okay, so E stands for element, half of integration of sigma t, that is a stress t, strain into dV. Okay, so here the where strain is equal to what, the change in deformation, that is do u by do x. Okay, so but here the 2d one node number 1, node number 2, that is acting opposite. So let us consider minus y, that is a deflection d square v by dx square. Okay, and so we know the formula, stress is equal to this Young modulus into strain. Okay, so we have the strain value is equal to this, that is minus y d square y by dx square, substituted in this equation. Okay, so now so this ey minus ey d square v by dx square you substitute in the this equation, that is what, the strain energy, the sigma t value. Okay, you are going to get strain energy is equal to ei by 2 integration of 0 to L d square v by dx whole square to the power of whole square. Okay, dx. Okay, so now so this what, by substituting the this values, let us assume this d square v by dx square values, let us assume c into q. Okay, so c is nothing but constant. Okay, so matrix of c, this that c into q. Okay, so substitute this in this equation. Okay, so half of what, ei is a constant, Young modulus and moment of inertia. So in place of this we are going to substitute this equation. Okay, so whole square again. Okay, so which is equal to, again simplify this, half of integration of 0 to 1. So this qv, so this q is some constant. Okay, so qv and matrix of this ei c transpose c into c and qv. Okay, so now you rewrite this equation, half of this what, this transpose of q e I transpose k, nothing, this is nothing but what, the stiffness matrix, that is element stiffness matrix. Okay, so which is denoted by k e is equal to q e. Okay, so k stands for, which is equal to this, so k e stands for element stiffness matrix. Okay, give equation number 2. Okay, so now we have the element stiffness matrix for what, this is integration of 0 to I, so ei c transport c into dx. Okay, so now so here minus integration of minus 1 to 1, you just go on integrate. So minus element number minus 1 to 1, so that is what, the zeta value is maximum only 1. Okay, so that is minus 1 to 1. So ei transpose of c. Okay, dx nothing but what, so that is a change in value. Okay, so that which is equal to L by 2 d zeta. Okay, so where the rigidity ei is moved out of the integral if it is constant over the beam element, and substituting the value of c here from the above equation, so we are going to get this value. Okay, so c value is equal to 4 by L square. Okay, so here just to substitute the c value. Okay, the rigidity Young, okay, that is Young modulus and moment of inertia is moved out of the integral. Okay, so this, if you remove this, okay, you have to this the if it is constant, okay, the beam element, and substituting the value of c. So here substituting the value of c is equal to 4 by L square, so do square do zeta square n1 n2 n3 n4. Okay, so these are nothing but what, the change in, that is what, the change in the given beam element. Okay, so n1 n2 n3 are the shape function. Okay, so already we derived this n1 n2 n3 n4 values. Okay, substitute this n1 value, so we have the n1 value is like this, n2 value we already derived this, n3 value, n4 value. Okay, so already we derived in the previous lecture video. So the shape function for this what, the beam element. Okay, substitute this n1 n2 n3 value in this equation, that is c is equal to 4 by L square. So after substituting in this, after simplification, so you are going to get this, that is 6 zeta by 4 minus Le 1 minus 3 zeta by 4 minus 6 zeta by 4 Le 1 plus 3 zeta by 4. Okay, this is about the c value. Okay, so again I re-simplify that. Okay, 1 by L square. Okay, so just to take here, do simply Le, take the common, this Le get going to cancel, so remaining is what, the 1 by L square, 6 zeta minus Le 1 minus 3 zeta minus 6 zeta Le 1 plus 3 zeta. Okay, so now this equation you write in the what, the matrix from. Okay, look at here, so 1 by L square, so 6 zeta. Okay, so minus 1 by 3 zeta Le. Okay, minus 6 zeta, and this. Okay, 1 by Le square, so this what, write in the matrix form. Okay, 6 zeta so this is a minus. Okay, so if you cross multiply means you're going to get the same value. Okay, so write down this 1 by LE. So this is right in the matrix form. Okay, so this one you have to write in the transpose. Okay, so C value, you know the value C is equal to what, this one, or the same values you have to write here. Okay, C transpose C. So C value you already calculated right in this matrix form. So C value you already calculated this right on. Okay, so multiply this and this. Okay, so L to the power of square, L square nothing but 1 by L to the power of 4, 6 into 6, 36 zeta square. Okay, so like that you have to multiply first row first column, second row first column, third row first column, fourth row first column. You are going to get 4 into 4 matrix like this. Okay, so after multiplication this. Okay, so now you integrate. Okay, so integration minus 1 to plus 1 zeta is equal to 0, and integration of minus 1 to zeta square is equal to 0, and zeta cube d zeta is equal to 0. Okay, so this zeta square, zeta cube, if you substitute the values 0 in this equation, so you are going to get this equation. Okay, so that is 2 by L to the power of 4, 12 6L. Okay, so this equation you are going to get. Okay, so now substitute this 5.43 equation in 5.38. Okay, so this what the integration C transpose C. Okay, substitute in this 5 point this in this equation. Okay, so if you substitute here, okay, in this equation, what you are going to get this, that is K is equal to EI by 2, so 2LE by L4. Okay, so substitute those values, so you are going to get this. So this 2 get cancelled, LE going to cancel, L cube will be remaining in the denominator. So finally you are going to get K is equal to EI by L cube. So 12 6L minus 12 6L. Okay, 6LE 4LE square minus 6L 12LE square, and minus 12 minus 6L 12 minus 6L 12 square minus 6L 4L square. Okay, so this equation you are going to call as element stiffness matrix for beam element. Okay, so with the help of shape function. Okay, Hermite shape function. Okay, so this in examination you can solve any one method. Okay, either using shape function or Hermite shape function. Okay, so this question is very important to solve the numerical problems on beam element, that is in module 3. Okay, so you have to remember this equation. Okay, so how you remember the formula for element stiffness matrix for what, 1D bar element and the truss element, and one more is what, beam element. Okay, so like that you have to remember this formula. Okay, again you have to derive the element stiffness matrix for torsions also in upcoming lecture video. Okay, so here the main thing is you have to remember this. Okay, integration of minus 1 to 1 zeta. Okay, so this is a constant term going to get 0. So integration of minus 1 to plus 1, if you integrate and substitute these values, you are going to get 0 values, and minus 1 plus 1 integration of zeta cube d zeta, which is equal to 0, means okay, this zeta and zeta square zeta cube is substitute in that equation. So here, so you are going to get this. Okay, so 12 6LE minus 12 6LE 6LE 4LE square minus 6LE 12 LE square. Okay, so this value is substitute in the equation number 3.8, that is 5.3.8. so you are going to get EI by 2. So this 2 get cancelled, so remaining EI by L cube will be there. So okay, so this is remaining. So this equation you are going to call as element stiffness matrix for beam element. Okay, so this equation is very very important. Okay now, so here one more you have to, okay, so this also you have to remember the shape function values. Okay, so n1 value is what, and n2 value is what, n3 value is what, n4 value is what. Okay, so here the C value is nothing but what, this is what, here this is, it belongs to at node number 1. Okay, so d square, the slope function. Okay, in the natural coordinate system, so dou square n1 by dou zeta square. So this 2 at node number 1 and this at node number 2. Okay, so you have to remember this n1 n2 n3 n4 are the shape function. Okay, so shape function nothing but what, the number of degree of freedom which is equal to number of shape function, that you have to remember in this case. Okay, so 4 by LE square, the 4 nodes will be there, that is 4 by LE square. Okay, so length element 2 element is the length is LE 4 by LE square. Okay, C value. So look at this, the rigidity EI is moved out of the integral. Okay, so suppose if you remove this C out of the integral, it is if it is a constant over the beam element, then substitute the value of C from the above equation. Okay, so you are going to get C value is equal to 4 by L square. So this at node number 1, at node number 2. Okay, so after n1 n2 n3, okay, after substituting the shape function values, so then it is very easy. You have to remember these values. Okay, 2 minus 3 zeta square plus zeta cube by 4, LE by 8, 1 minus zeta square plus zeta cube, 2 plus 2 zeta minus zeta cube by 4. Okay, this you have to remember, substitute again, simplify, you are going to get the element stiffness matrix for beam element. Okay, I hope you understand this. Okay, so here what you want to remember is this you have to remember. Okay, and how to remember this formula I already told you. Okay, so how to remember this formula, so first you have to remember this EI by LQ. First you have to remember these 4. Okay, so after remembering these 4, write as it is to, okay, this side. Okay, Right, as it is this side put negative sign. Okay, so put minus minus here. Okay, then once if you wrote this, so take down these values. Okay, so this value if you take minus 12 6 le minus 6 le 12 le square, so write this in this side but in opposite side, that is horizontal minus minus. Okay, so this is the minus minus, you have to put it minus minus, so this is positive. Here values are vertical, this is horizontal. Okay, like that you have to remember the element stiffness matrix for beam element. Okay, so like this you have to remember the element stiffness matrix for beam element. This equation is very important. Okay, so I hope you understand this derivation. Okay, thank you.